Pinball is really pretty simple. Now, I'm actually not going to cover how to physically work on the game. I'm not going to cover how to replace the coils, how to mechanically work on the game. That's honestly pretty simple, and anybody that's looked at the game at the inside of a pinball machine really knows how to physically do those kind of things. What I want to concentrate on instead is how to work on the electrical part of it. Specifically, there are three things that I want to cover. Number one, the solenoid circuits. The solenoid drivers. That's really the coils. Number two, the switch circuit, which in a pinball is actually called the switch matrix, and I'll explain a little bit about that. And finally, I guess more than that, I'm going to do four things. The lamp driver circuit, and then finally, number four, the high voltage power supply, because the high voltage power supply in this pinball, this F14 that we have here, does have a problem in it, most likely a bad Zener diode, and we'll talk about that as well. In order of how often they fail, solenoid drivers are definitely number one, switch number two. It's really a toss-up between lamp drivers and high voltage power supply. In fact, perhaps the high voltage power supply actually fails even a little more often than the lamp drivers. But let's start out by taking a look at the solenoid driver circuit. In the pinball machine, there is a power supply for the coils. In the older Williams games, like this one, it's about 28 volts DC. In the new games, what they call the WPC system, it's 50 volts. All the coils are 50 volts. In this game, all the bumpers and kickers and so on are 28 volts. Only the flippers are 50 volts. There's a separate 50 volt power supply that's right here on the board. This is only for the flippers. There's a flipper fuse here. This little power supply is only for the flippers. All the other coils use 28 volts DC. All the new games, all the coils are 50 volts DC. The higher the voltage, the more powerful they're able to make those flippers, basically. Well, that 28 volts DC is connected to every coil in the game. There's a wire that goes from coil to coil to coil in the game that carries that voltage, the solenoid power supply voltage, to each coil in the game. A little later on, we'll take a look at underneath the play field, and I'll show you those things. To energize each coil, there's a bunch of transistors here on the board. And right down here, there's a group of transistors down here on the board. And up here, there's also another group of transistors. Let's take a closer look at those. These are all TO220 transistors, TO220 package. These are the TIP 122s. These guys right here.
That's a pretty common one to use throughout them.
Yes, you can use it for any pinball. Also, there's another group of 6 up here. These are what they call the special solenoids. This group of 6 is used for the bumpers and the kickers. Solenoids where you need a very fast action. As soon as the ball hits those things, the bumper or the kicker, we want to have an instant reaction. And so those are what they call the special solenoids. The other ones detect a switch closure. The computer says, oh, well, I think you've made that switch. Okay, I'll activate the target bank reset or whatever it is. So these are like special fast-acting ones. Actually, the circuit is really virtually identical, and we'll take a look at that in just a second. But each of these coils is connected to one of those transistors. It's connected to the collector of the transistor. Now, these are Darlingtons. I'm not going to draw them as Darlingtons because it just takes too much time. But they are actually all Darlingtons, and the emitter is grounded on each one of these things. When the computer wants to energize a coil, it turns on the transistor. We're going to look at the rest of the circuit in just a little bit. But when the computer wants to energize the coil, all it does is turn on the transistor. It puts a small amount of voltage on the base that turns the transistor on. Now, these are Darlingtons, so it really takes about 1.4 volts or so to turn it on. When the transistor turns on, of course, the collector is connected to the emitter. And the current flows from the 28-volt power supply through the coil, through the transistor, from collector to emitter and to ground. Notice, of course, that it's going in the direction that the arrow is going, number one. Number two, this is a ground switch, isn't it? This is a ground switch. The power is always connected to each coil. To energize the coil, we simply switch the ground in and out. When the ground circuit is completed, the coil energizes. When okay, that's bizarre.
That happened once before.
Yeah, I have a very bad thing on my. I have a bad connection, a bad switch on there. Anyway, see, now we got it. Now you guys got to go like this. See, you're gonna, and then it's gonna cut back to me, and we'll keep going on. When the computer wants to energize a coil, it just turns on the transistor activates, completes the ground circuit, and the coil energizes. When the computer wants to turn the transistor off, it just removes that base voltage, the transistor turns off, and the coil de-energizes. No big deal. Well, let's say that you get to the game and you have a coil that doesn't energize. It doesn't energize at all. There's a real simple way that you can test to see if the coil is good or bad, using just a clip lead. If I take a clip lead and ground it to the ground braid somewhere, and right here on the pinball there's a ground braid that surrounds the whole pinball right here. It goes all over the place. And I just have a black clip lead. Well, it doesn't have to be black, but I just have a clip lead attached to this thing. All I have to do to check to see if the coil is good is take the clip lead and touch the collector, which is the metal tab of the transistor. It'll energize either the lights or the coils, depending on what's hooked up to that particular transistor. Now, I'm not testing the transistor this way. I'm not testing the transistor. I'm only testing the coil, aren't I? And what I'm doing here is I'm taking the clip lead and shorting that guy to ground. If I short this collector directly to ground, I'm essentially bypassing the transistor, And if I do that, the coil energizes. I know not only is the coil good, but I got power to the coil, and the wire back to the board over here is good, too. Now, you can do it under the play field as well, and I'll raise this in just a little bit and show you. On the pinball machine, you have the two solder lugs. One of them will be connected to the power wire, to the positive, and the other one goes to over here to the computer board. I can take that same clip lead and ground one side of the coil. It will also energize the coil there. So that's, if you try that and the coil does not energize, you probably have a bad connection somewhere. Maybe the coil is open. You can turn it off and check the resistance of the coil. Coils generally have a pretty low resistance, anywhere from 8 to 10, 15 ohms, something like that. Regardless of what the resistance is, if it is open, then the coil is bad. If you find that the coil is open, that is, you have a broken wire on it somewhere, don't throw the coil away before you try to find that broken wire. Peel the paper off the coil. Just peel the paper off the coil. And you have a 50-50 chance of being able to fix it, because one of the coils naturally is wound around the outside of the coil, and it goes to one of the terminals like that. The other one goes to the inside. If the one on the inside is broken, you can't fix it. But if this wire is broken right here, you can just unwind it a couple of turns and resolder it on there, and it'll be fine. Coils are expensive, so you don't want to just throw away a coil because it's not working. Now, a coil that doesn't work is really not very common. Most of the time, the coil's burned up. Right, Shirley? Most of the time, the coil burns up. In fact, you've got one right there. Let me just grab that. Let me grab this one, too. Oh, thanks. Most of the time when a coil is bad, it's physically burned up. You can see that it's visually burned up, and that's usually what happens. And what causes the coils to burn up, other than the flipper coils, which we'll talk about in just a little bit, what causes like the bumper coils and so on to burn up is that the transistor fails. The transistor shorts collector to emitter, like we've seen a bunch of times, and stays energized all the time and burns up the coil. So naturally, when you get to a game that has a burned up coil, the first thing you want to do is replace the coil, obviously. And what you'll find is that almost without a doubt, the transistor associated with the coil is bad. The transistor associated with that coil is bad. Now, many of the pinball machines, most of them in fact, have a fuse in here in line. And this fuse is usually a 2.5 amp slow blow fuse. This is really important. It's an important fuse. The reason that the fuse is there is this. Normally these coils draw, let's say, about 3 amps or so when they're energized. A slow blow fuse, like in this case a 2.5 amp slow blow, will blow if you exceed 2.5 amps, but it doesn't happen immediately. It takes about a second or so for it to blow. By putting a 2.5 amp slow blow in there, when the coil energizes normally, like a bumper, it just bumps for a fraction of a second and then it unbumps, right? It just energizes and then de-energizes. It's not energized long enough to blow the fuse. But if the transistor is shorted, the coil remains energized continuously. We slightly exceed the rating of the fuse, and the fuse opens up. The fuse opens up to protect the coil from burning up when the transistor is bad. Theoretically, that's what it's for. You have to replace these fuses with 2.5 amp slow blows. I was on location once working on a pinball machine, and you got to try to be observant when you're working on a pinball machine. Normally, a slow blow fuse looks something like this, or some of them look like this with the spring down here like this and like that, slow blow fuse like that. And that's what's supposed to be in there. And I'm looking at the pinball, and just visual inspection is very important, especially in a pinball machine. So I'm just looking around, just opening the thing, just looking around, and I see this fuse, and it doesn't look like this. It looks like this. Someone had put a 25 amp fuse in there instead, not seeing the decimal point. And if there had actually been a failure in that circuit, it would not only have fried the coil, but it would have burned up the wiring and everything. It would have really made a big mess of the pinball. So 2.5 amp slow blow is what you want to put in there. So that's a bad deal. Now, here's what usually happens. Here's really the scenario when you're working on pinball machines. You get to the pinball machine, and well, in fact, let me demonstrate this for you. This has probably happened to you. Here. you get to the game, you turn it on, listen. As soon as you turn it on, you hear a coil energizing, right? Okay, that's a transistor failure. That's a transistor failure. Here's a really cool shortcut to find out which transistor it is. On the pinball machine, there are connectors here that obviously connect the transistors to the coils. Disconnect those guys. Wrong one. Disconnect that one. Let's see if that's the one. Disconnect them until the problem goes away here. Okay, doesn't energize anymore. With the thing disconnected, and it's turned on, reconnect the connector, and what you're looking for here is a little spark. See if I can focus this. In fact, let me get it from the other side here. You're looking for a little spark. Watch. See the little spark? See which pin sparked. Whichever pin sparked, if you just follow the trace back on the board from that pin, it's that transistor that's bad. That means you don't really have to have a schematic diagram to figure out which one's bad. So that's a real fast way to do it. Okay. There's another quick way to do it as well, and maybe it's even faster. When these transistors fail, they generally have a collector to emitter short. I mean, that's why the coil's staying energized all the time. It has a collector to emitter short. With your meter set on the diode test range, or the continuity beeper, ground the black lead to just stick it in one of the ground braids somewhere. That's on the side of the, whoops, hey, come back over here. Like a ground braid that's on the side of the cabinet somewhere. And touch, with the power off, touch the collector tabs of the transistors. When you get to the bad one, it shows you the short circuit. I'm just touching the collector tabs. That's even faster, really. And if the transistor really does have a collector to emitter short, that'll pick it up. Sometimes it's not as obvious this way, but most of the time it is. So in fact, you can just go down the line and really just like touch the transistors, one at a time like this. And when you hear it beep, that's the one that's bad. So that's really fast. That's a really fast deal. Okay, so, and again, this is when you get to the game, you turn it on, and it makes all the game sounds and plays and everything, but one coil stays energized all the time, or one coil has been completely burned up, and you replace the coil, you probably have a bad transistor as well. Well, let's say that you've done this. Look in your book now on page 27. And on page 27, there's a partial schematic diagram of the output circuit, the solenoid driver circuits in these things. Let's say, for example, that you have found that transistor Q17 is bad. And they're all labeled here on the board. You can't miss them. Let's say you found that Q17 is bad. And you've replaced the coil, let's say. You've replaced Q17. You turn the game on now, and now it doesn't energize at all. Where we had a problem before where it was staying energized all the time, now the coil never energizes at all, never ever. Well, gee whiz, take a wild guess. If Q17 was bad, and you can see the emitters grounded, and there's the collectors going to the coils. If Q17 was bad, you replaced it. It was completely shorted out, wiped out, and now it doesn't work at all. Gee whiz, what other transistor do you think might be bad here?
13.
Q13. Do you see how Q13 is used to drive Q17? What happens is the failure just works its way back. In other words, Q17 fails, shorts out, and what often happens is someone finds the blown fuse, before they change the coil, before they change the transistor, they stick in a new fuse. Now it moves back to the next one and blows Q13. And it's real easy to find those things. Whenever you look at these the driver transistors, you'll see that they're actually in pairs. Sorry, edit. Okay. When you look at the transistors, you'll see that they're in pairs. You see the driver transistor, and then right on top of it, there's the pre-driver transistor, like Q71, Q70 there. Or in the case of the one we're looking at, here's Q17 right here, right? And Q13 is right here. Q17, Q13. A lot of people just change them both. A lot of people, when they're, as long as they're in there working on the thing anyway, they simply change them both at the same time. That's okay. You can do that. There's nothing wrong with that. The transistors are only like a nickel or a dime or something, depending on where you get them anyway, the little ones, the 2N40/401s. So a lot of people just change them in pairs automatically. I always figure if it ain't bad, why replace it? You might as well just test it and leave it in place. Now, it's really a hassle to pull out this board. There's just a whole mess of connectors all over this board, which is called the CPU board, Central Processing Unit. Millions of connectors. There's a little shortcut that I do sometimes, and admittedly it's not terribly professional, I suppose, but it's really fast. It'll take you a good 20 minutes minimum, maybe even more than that, to pull the board out, change the transistor, and put it back in. What I often do is this. Here's the transistor. And it's sticking through the board. Now here's the PC board here. You know, the legs go through, they come out the bottom, they're soldered in on the bottom, obviously. What I will often do is cut off the transistor, leaving the legs sticking out like that. Then I will carefully, and I mean really carefully and quickly, tin each of the legs. Put a little tiny drop of solder on it. That's called tinning it. Just use your soldering iron, a little tiny drop of solder on each one. Then I'll take the new transistor, put a little tiny drop of solder, you get where I'm going on this, on each of the legs of this thing, and then carefully, holding the new transistor up, just touch it with a soldering iron, like that. You really kind of have to be pretty good at soldering to be able to do that. You have to do it quickly, and of course, you cannot bridge solder between the legs. And you see that they're very close together. So it does kind of leave this transistor like, hanging off the board, where it's like you see this transistor that's hanging out an inch off the board. So yeah, it doesn't look that great, but it really saves a tremendous amount of time. And so I'll do that sometimes. It's not the greatest thing in the world, but it's really fast. Jeff, do you have a question?
No, just piggyback. It's almost like a piggyback.
Well, it's almost like a piggyback, except that you actually have removed the old transistor. Okay? All right, well, let's go back to the schematic diagram again on page 27. Let's say you've changed Q17. It was bad. You've changed Q17. You change Q13. You fire it back up, and it still doesn't work. Well, this is not an uncommon failure. The integrated circuit has been blown. Do you see where it says U18 there? Okay, that's an integrated circuit, and that's this integrated circuit right here. It's one of those TTL integrated circuits that we discussed earlier. And there it is, U18. There it is, U18, integrated circuit number 18. It's a type 7408. And that integrated circuit, you can see the wires, the leads coming right from it, driving the pre-driver transistors, right, like that, which then drive the main transistors. Well, it's not uncommon for that integrated circuit to be bad. Let's take a look at that integrated circuit. This is one that I carry with me. In fact, believe it or not, I consider this to be an in-the-field repair. I don't really have anything with me in the shop that I don't have in the field other than a little peace and quiet, to be honest with you. And so I change chips in the field all the time. It's not terribly difficult to do. Let's go back to that integrated circuit. We discussed these ICs before. These integrated circuits are TTL, transistor-transistor logic. In this particular case, it's a type 7408. It's technically called a quad AND gate. I'm not going to get heavily into digital electronics here, but in a nutshell, here it is. Remember that this corner is the plus 5 volts DC, what the really truly hip and professional technicians refer to as the VCC. And then kitty corner over here, this is pin 7, this is pin 14, is ground. And so we've got 12 other pins. These gates are set up like this. There's 1, 2, 3, 4, 5, 6, 13, 12, 11, 10, 9, 8, like this. The schematic symbol for this AND gate is just like a letter D here, basically. There are 4 individual gates in this one integrated circuit. That's why it's called a quad AND gate. Quad, 4, right? Like a quadrilateral 4. Anyway, there are 4 completely independent gates. In fact, the only thing that they share is the common power connection, and they're in the same chip. But in fact, it's entirely possible, and it happens all the time, that one of the gates is bad, but the other 3 are perfectly okay. It happens all the time. They're just completely independent things. Well, anyway, remember that these are TTL. Now, I know it doesn't matter how these things work at all, but the output, which comes from the curvy part of the D, goes to the transistor, the driver transistor, which then drives the main Darlington transistor. So this is basically the circuit. When the Darlington shorts out, blows the pre-driver, sometimes it'll work its way back and blow the integrated circuit. Well, the little trick that we used to find bad ICs before works perfectly on this. And in fact, this is really where I use it more than any other place. To tell if the IC is bad, put your meter on the diode test setting. This time, we're going to ground the red meter lead. Just go on one of the ground braids that are on the side of the game there somewhere. Just stick the red lead right on the ground. And using the black meter lead, probe the pins of the IC. For instance, we're surmising that Q17 was bad, which blew Q13. So do you see how it says U18, pins 1, 2, and 3? Each pin that you probe should show you a normal junction drop. Pin 1, 0.57. Pin 2, 0.48. Pin 3 is really the one you'd want to test, really, because that's the one that's connected to the bad transistor, isn't it? It says 0.56, it's good. If it was bad, it would show you something extremely low, something much lower than that. This works really, really well. I mean, it works great. And just to kind of show you up close for those of you that if you want to see it really close here, let me just do it up incredibly close here. Again, the red meter lead is grounded. All I'm doing is taking the black lead, which is the bizarre thing about this test. And for instance, here's U18, pin 1, 0.55. Pin 2, the meter says 0.48. And pin 3, the one we really wanted to test here, 0.53. Well, that's really pretty darn easy, isn't it? I mean, there's really not much to that. I mean, that's an awfully easy test. The thing that makes this test really cool is that here's what most people do. Most people, when they want to check the integrated circuit on a board, will use something called a logic probe, which is a thing that shows the ones and zeros, the digital logic, and shows you blinking lights. And you have to know exactly how the circuit works to use that. And you have to have the power on. Here's what happens to most people. Most people, they get to the game, the coil is burned up. They change the coil. Turn the game back on. The coil stays energized now all the time because the big transistor, the Darlington, is shorted. They pull the board out. They change the Darlington transistor. They put the board back in, putting all those millions of connectors back on it. Fire the game back up. Now the coil doesn't work at all. They pull the board back out. They test the transistor, the pre-driver, the 2N4401. Put the board back, finding it to be bad, they change it. They put the whole board back in, put all the connectors back in, fire it back up, still doesn't work. Put it back in, put all the connectors back in, and with the power turned on, using the logic probe, they will probe the pins and say, well, I think that, because I know how to use a logic probe and I'm really bitching, that the IC is bad. Then they'll pull it all back out again, change the IC. Well, as long as you have the board out, test everything all at once. And by using this little trick, you can do that. In fact, you don't even have to have the board mounted in the game. You can simply ground the red meter lead to this pin right here. Whoa, hey, over here. Thank you. You can simply ground the red meter lead, remember that's what's weird about this trick, to pin 7 of one of the ICs. It doesn't matter which one. You'll be grounding it that way. And with the board right out in front of you on the bench, power off and everything, probe the pins, find the IC to be good or bad while you've got it out. Do it all at once. Check the Darlington transistor, the pre-driver, check the IC, change everything that you need to change all at once, and whip it back in, and that's all there is to it. Pinball boards are a great way to break into logic board repair. If you want to eventually get pretty hip and start doing some logic board repair, you can see how simple this is. This really is simple. It's a great way to start to learn and to boost your confidence. And the little meter trick of finding bad ICs by grounding the red lead and probing with the black lead to look for those junction drops, I tell you, that has worked so well for me that I have virtually abandoned conventional troubleshooting. I don't sit down with the oscilloscope and do all that stuff anymore. The only thing I do is almost always is use the meter. Yeah, Ken?
So if you were to ground if you were to reverse those leads, you would always get open.
Exactly, you would get an open reading. The reason why I ground the red lead is that I see the junction drop, meaning that my meter probe is on that pin. I know I'm making good contact. I'm seeing something. That's why I do it. Turn to page 31, please. And let's take a look at the switch circuit, which is called the switch matrix. And you see on the top of the page here, switch matrix table. This one happens to be from police force, but they're all the same. In a video game, the switches are pretty straightforward. In a video game, you have the logic board, and each switch has its own input line. The other side of all the switches is grounded in a game. In a video game, you know that the control panel, there's a wire, a ground wire that goes from switch to switch to switch to switch on the control panel. And these switches, like the move up, move down, start, whatever the buttons happen to be, go to the logic board, and on the logic board, of course, since it's made of nothing but integrated circuits basically, there's an IC that takes those inputs and tells the computer what you're doing. The way it works is really pretty simple. When you have the switch open, that is when you are not depressing the switch, the voltage on this wire will be around 5 volts or so. When you close the switch, when you press the button or move the joystick, that grounds out that line and it goes to 0 volts. When the IC sees that it drops from 5 volts to 0 volts, it says, oh, you've activated that switch, and I better do whatever it is I'm supposed to do. Well, that's great in a video game, because in a video game, you might have a maximum of 24 switches or so. You know, in a video game, there's really not very many switches in a video game. And so, I mean, even in something like Street Fighter, where you have, you know, the 6 buttons on each side and all that kind of stuff, you've got a maximum of, I think, 24 switches or something like that. 24 wires, 24 inputs. Oops. Okay. But in a pinball machine, you can have up to 64 of those things. You can have up to 64 switches. And so we would need a bundle of wires this big to handle all 64 wires. We'd need 64 inputs on the board. And so it's impractical in a pinball machine to do it this way. Instead, in a pinball machine, we have something called the switch matrix. The switch matrix. And as you see in your book there, the switch matrix is actually 8 by 8. I'm going to draw a 4 by 4 matrix here just for the sake of simplicity. The switch matrix is divided into rows and columns. Rows and columns. Rows that go horizontally, columns that are vertical. And there's a switch between each row and each column, like this. Now, there's also a diode in there, and I'll talk about the diode in just a little bit, but let's look at the switches first. Between each column and each row, there's a switch. And the switches are the switches on the playfield. Here's the way this works. Now, I'm actually going to kind of lie to you first and tell you, I'm not really going to tell you the truth first. I'm just going to give you an impression of how this thing works, then I'll tell you how it really works. These columns are outputs from the computer. The switch columns are outputs that come from the computer. Momentary pulses that the computer sends out one at a time. The rows are inputs back into the computer to the CPU, the central processing unit. The columns are outputs that come from the computer. The rows are inputs that go back into the computer. Here's the way it works. One at a time, the computer sends pulses down each column. One at a time, and it does this about every thousandth of a second, about every millisecond or so. Bam, 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 bam. It does this over and over again. There's really 8 columns, 1 through 8, 1, 2, 3, 4, 5, 6, 7, 8, 1, 2, 3, 4, 5, 6, 7, 8. Over and over and over again, it sends these pulses out. If a switch is closed, let's say the ball hits this switch right here, and it's closed. That pulse that comes out of the column will travel along this switch and be sent out the row back to the CPU. That's how the computer knows which switch has been activated. Here's really basically the way this thing works. One at a time, the computer is saying like, hello, 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 down each of the columns. And it starts over again over here. Hello, 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 hello. Then it listens down the rows. And it's listening, it's listening, it's listening, listening for an echo. In other words, if it's over here, and let's say I say, the computer says, hello, down here. And over here, it hears an echo right here. Switch Jeff must be the one that's activated, huh? I mean, if it sends a pulse this way to Jeff there, and switch Jeff here is closed, and the echo comes back here, obviously that switch is the only one that satisfies that. And that's the way this thing works. One at a time, it sends the pulses down. If the switch is closed and it receives an echo down this row, the computer knows which column it's putting it out at all times, obviously. And when it hears the echo out here, it knows that that's the only switch that's closed. Now, this is all happening very, very fast. In fact, it's happening so fast that not only does the computer know that that switch has been activated, but it has a chance to go back and check it 2 or 3 times. The first time it detects that switch is closed, it doesn't even give you the points yet, or activate whatever it's supposed to be in the game. It registers that the switch is closed and says, I think that switch is closed. Maybe it's a false closure. Maybe somebody just banged on the game. Let's double check that. And the next time around, it checks it again, a tiny fraction of a second later. Even though we're only talking about the ball, boink, hitting a target, it has enough time to check it a couple of times. And when it's checked it the second time and sees that the switch is still closed, it says, valid closure, here's your points, or whatever. So it does that over and over and over again. Does that make sense? It's really very simple. It's called a switch matrix. Now, the reason that the diodes are here, and if you look at the schematic diagram on page 31, you see the diode in line with each switch. The diode is a steering diode. Or is that S-T-E-A-R? No, that's mo, isn't it? Steering? Is that how you spell steering? Okay, hey. Yeah, just call me Dan. P-O-T-A-T-O-E, potato. All right. Anyway, the reason that diode is there, it's for isolation. Without the diode in there, if I had, let's say, a switch closure here, not only will the pulse appear on this one, but if I have, let's say, 2 switches closed at the same time, which is entirely possible, that column drive will also appear on this one as well. And so the diodes are important. Whenever you work on a pinball machine, if you ever change a switch on it, on a pinball, you must make sure that you have the diode on there properly. Four balls. And here they go. Oh, they're staying put. Amazing. When you look at the switches, you'll always see that there are some diodes in line with the switches. Like there's a diode right here. Diode right there. There's another diode right here. See, on every switch, there's a diode. There's a diode on the switch right there. Every switch has a diode. If those diodes are not properly installed, you can confuse the heck out of the game. It can really, really confuse the game. So whenever you replace a switch or work on a switch or whatever, see the way the old switch is connected. Make sure that you connect the new switch the same way with the same diode and all that stuff. Otherwise, it can really confuse the heck out of the game. So I almost never see these diodes fail, by the way. In fact, the only time I've ever seen it fail is when it's been physically broken. Mostly that happens when somebody pulls up the prop stick on the game and whacks a diode on the way up or something like that. Or when they close it back down or something like that. It's usually some physical abuse in any case. Well, the way this really works is that connected to each column is a column driver transistor. Connected to each column there is a transistor connected like this. Boy, is this starting to look familiar or what? What is this thing? What is this? The ground switch, isn't it? Right? Remember? The transistor simply goes to ground. Just like we've seen a bunch of times. Ground switch, same thing. What really happens is, one at a time, these transistors activate, grounding the column. And that ground is actually sent out to some other chip on the board. Well, here's the bottom line. It's very common to have switch failures in a pinball machine. It's really common to have switch failures in a pinball. It's also very common on F14 to have these wires get caught up on it. Okay. Now this looks good. And what causes the switch failures is the column driver transistors. These column driver transistors fail all the time. It's really common. Let's take a look at them. And they're really easy to spot. You always see a group of 8 transistors, little transistors. Here they are right here. These 4 here, these 4 right here. These are the switch column drivers. You see Q49, Q45, 44, 43, Q42, and so on. When you have a failure, when you have a switch failure, if you just have one switch that's bad, the self-test in the game shows that to you. Whenever you turn on a pinball machine or put it in test, depending on the game that it is, it has a switch test that goes through and tells you if you have any stuck switches. Basically what the switch test is doing is it looks for a switch that has not been activated in X number of balls and says, well, that switch is bad. Yeah?
Like mine has 2 switches that's off.
Just 2?
Yeah.
Okay, if you have just 2 switches that are bad, then you just look at those switches and physically repair the switches. But if you have 8 switches that are all bad, you have a column driver that's out. Check it out. Look at the chart on page 31. And let's say, for example, that the self-test in the pinball has told you that the following switches are bad. 25, 26, 27, 31, 32. What's common to all those things? Do you see how they're all in column 4? Well, look in the upper right-hand corner of column 4. Do you see it has a transistor number there? What is that? Q48. Okay, I guess I better change Q48. I guess it's bad. That's all there is to it. Williams is really the greatest company in the world, I think, as far as service is concerned. I give Williams the A#1 Randy Fromm's Award of Excellence because they make your job real simple. In fact, this chart is always inside the back cover of the book that comes with the game, which is actually missing in this one. Do you have it in this F14 here?
No, I didn't bring one.
Okay.
Just 2 switches.
Okay, it's always, the switch matrix table is always inside of the back cover. So it's real easy to find, yeah.
Also, they have a small operator.
Yeah, there's a little book, a little handbook that comes with games too, and that's really handy. So don't agonize over it. If you have a number of switches, if you have 8 switches that are all bad, or you look at the switches and they're all related to one column, it's the column driver transistor that's bad, and that's really all that ever goes wrong. If, for instance, though, you have a number of switches that are bad, but not all of them, for example, let's look at column number 1. No, that's not. Let's look at column number 7. And let's say that it says that the switches that are bad are 49, 50, and 51. But the other ones it says are not bad. Well, those are all related to something. They're all related to that column. It cannot be the column driver transistor, can it? Since some of them are working, it can't be the transistor. Well, also, if you look at the top of the column, do you see that it's a green-violet wire? See that? All you have to do is look at the different things that are working, the N, the U, the G, whatever ones are working, follow that green-violet wire around. At one point, you'll see that the wire is broken off, because that's what happens. If you have a problem where there's a number of related switches that are bad, but it's not all of them, you simply have a broken wire. When you look at amazing, it stayed put. When you look at those, the switches, you'll always see that there is a wire that goes in this way, like here's a white wire with an orange stripe, comes in here and goes out to the next switch. You see this all over. Here's green with looks like a brown stripe. Comes to this switch, and then goes to the next one. It's called daisy chaining. Well, one of them will just be busted off. You'll see the wire will go to one, and it won't be going to all the rest of the, all the rest of the switches that are in that line. And you see this all over the place on all the switches. Here's the same color wire. In fact, the green brown or whatever it is. So all you have to do is follow that wire around. Just look at the switch matrix table. See which switches are attached to that color wire. Just look at each one. You'll see that there'll be a wire busted off of one of them. So when you have multiple switch problems, if they're related to something, look for that wire color, whether it's the same, whether they're related to a column or a row or whatever. Yeah, Ken.
So having one wire off doesn't kill that whole circuit?
It kills everything from the point where it's fallen off on. If it has fallen off the first switch, they'll all appear to be bad.
So it would kill, say 5 through 5 through.
Perhaps. They don't go, the wiring is not in the same order, by the way. The wiring is in physical, the most logical physical order, but the wiring does not necessarily go in line from one to the other. So you just look at each one and you see. Only once have I had a problem where all the switches were disconnected on a bad CATS, way down here in the bottom of the game, right down here, where the cable first snakes in. The main cable first snakes in from the back box. It was broken off right at the very first switch, and in that case, all 8 were bad. Well, the first thing I did was change the transistor. I was misled, wasn't I? Gee, all 8 of them are bad. It must be the transistor. I changed the transistor. No change. Well, the only other thing was bad connection, and it's most logical that it would be down there at the bottom down here because that's where it all starts out. I mean, that's where and it also flexes the most down there. Yeah, Andy.
So that's why you check the line first for the switch?
Well, I checked the transistor first because that's so common. It said all 8 are bad. I never had it not be just the transistor. It always has been just the transistor, except for this one bad CATS. It was a brand new bad CATS, too. It had just come from the factory. We put it on location, and whoever set it didn't realize that it wasn't working right. Our truck driver didn't realize that that's what it was. On every coil, you do see a diode, on the pinball coil like this. Flippers have 2. This one has 1. Here's what that's for. On every coil, there is a clamping diode. That goes to the positive voltage. There's the clamping diode. It's a regular old diode. It's a 1N4004. And of course, this guy goes to the transistor, which goes to ground, like that. This diode's real important. The diode protects the transistor. Without the clamping diode on there, the transistor will probably be destroyed. Now, if you look at the way the clamping diode's set up, normally you would never expect that to conduct, would you? Because the current doesn't go through a diode that way. It only goes through, the current's going to go through the coil like this, but it's not going to go through the diode. Well, here's the reason that the diode is there. When the transistor is energized, when it's, shorted collector to emitter, current flows through the coil, through the transistor to ground, just like that. When that happens, of course, the coil builds up a very large magnetic field, like that. When you de-energize the transistor, when the computer turns the transistor off, that magnetic field collapses very fast. When the magnetic field collapses, it acts like a generator. The coil acts like a generator. And the voltage right there will want to rise to a couple of thousand volts, really. Well, we can't allow that to happen because that'll blow the transistor. It's only like an 80 or 100 volt transistor. With the diode on there, that cannot happen. Because let's say, for instance, we have a 28-volt power supply. As soon as the voltage right here goes to 28.7 volts, we now have more voltage on this side than the other, don't we? The diode does start to conduct and essentially shorts out the coil, shorts out that high voltage spike. Instead of allowing the voltage to rise to 2,000 volts, it can go no higher than 28.7 volts in this case. That's real important. That diode is really important. Without that diode on there, several things can happen. One, you could blow the transistor that's in the coil driver transistor. Number two, the high voltage spike that would be created by the fact that you don't have the diode in there can cause the game to freak out. It does things like it'll shut the game off, or it will add points or take points away or tilt the game or do all kinds of wacky things. You don't even know what the hell it might do. Now, so does that make sense? You have to have the diode on there. The diode, the cathode of the diode, always connects to the positive power supply. When you look at any coil that has a diode on it, like this coil right here, for instance, if you look at this carefully, here's the power wire. And I can tell it's the power wire because it has two wires hooked up to it. Remember, the power goes from coil to coil to coil like that. And there's the diode, and you can see that it's hooked up to the cathode of the diode. Really important. You know, here's where the power comes in, the plus 28 volts, and there's the cathode of the diode right there. Yes, Shirley.
Sometimes you have coils that have 3 leads on it. What's the middle one or the third one for?
That's the flipper coil. The flipper coil is the only one. I don't know what that weird one is you have in that old Bally game, but the flipper coil is the only one that has the 3 leads and the 3 diodes on it. That's because there are 2 different windings on the flipper coil. The flipper coil has 2 different coils in it. One's called the pull-in winding, one's called the hold-in winding. And old coils were like this in series. There are new coils that like these that are parallel wound, but regardless of that. The pull-in winding has very low resistance. The hold-in winding has a higher resistance. We need to have both coils so that when you depress the flipper button on the game, you get a very hard shove to knock the ball up, but we don't want to burn up the coil when it's held up. So the hold-in winding has a higher resistance. It allows the coil to stay up, the flipper to stay up and hold up so catch a ball or whatever, but not burn up the coil. Well, there are a couple of diodes on a flipper coil, usually 2 diodes, 1 or 2, depending on the flipper. Well, here's a weird thing that happens, or that happened to me. If you have a problem with the flippers, let's say you get to the game and the complaint is that the flippers aren't working. Oh, here we go. There is, remember, a separate power supply for the flippers over here. And there's a fuse on it. There's a flipper fuse right here. You know, here's the entire flipper power supply. Here's the fuse. And you can see the bridge rectifier and the fuse, and there's even a capacitor there. Well, I have actually never seen the bridge rectifier itself fail, but the diode fails on flippers a lot. Let's say you get to the game and you find that you have a flipper that's not working. In this game, there's only one flipper fuse for both flippers. Other games, the newer games, have a separate left and right flipper fuse. So you get to the game and let's say none of the flippers are working, all right? You look at the flipper fuse, it's blown. You raise the playfield, you look at the flipper, the coil looks perfect. It's not burned up at all. you have a shorted diode. You have a shorted diode on the flipper. You cannot measure the diode on the flipper coil because the flipper coil is such a low resistance that it always appears to be shorted even if it's good. But you have a shorted diode. So here's what I do. First thing I do, I get to the game, I put a new fuse in. I fire up the game or put it in self-test, which also activates the flippers. And carefully and quickly, I try just barely tapping the flipper buttons. I mean, I just barely tap them. The reason I'm just barely tapping them is when I tap one of them, the flipper will flip, it'll work okay. When I tap the other one, I'll just see a spark and the flipper won't work. That's the bad flipper, obviously. I'm tapping it quickly because hopefully I won't blow the fuse that way, so I don't have to waste a fuse. So now I know, let's say, that the problem's on the right-hand flipper. Okay, I have a problem with the right-hand flipper. If the flipper looks perfectly good, the coil looks perfectly good, I simply cut the diode off. Cut only one end of the diode. Don't cut them both, because if you cut them both, you won't know which way the diode goes back in there.
Which end? Any end?
It doesn't matter. I'm just removing the diode from the circuit. I'm leaving one end on there so that when I put the new diode on, I know which direction it goes. If you put it backwards, it won't work, obviously. And then I'll try the flipper, and it will work perfectly okay. I'll try the flipper, and now it works perfectly okay. So I put in a new diode. Well, here's what happened to me. I got to a location, no flippers. Changed the fuse, tapped the buttons. I determined that this right-hand flipper is bad. I clip the diode off, I try it once or twice, it works. You don't want to keep trying a flipper without a diode on it because it sends those voltage spikes through everything and freaks out the game. Probably won't damage it, but freaks it out. So I put a new diode in, play a few balls, everything works, I leave, everything's fine. Next day I get a repeat service call, the exact same problem. Exactly the same, everything's exactly the same. So I go through all those same things again, thinking, wow, I must have had a bad diode or something. I don't know what's going on. I put the new diode in, everything works fine. Next day, repeat service call, same thing. This diode keeps failing. So now I'm really freaking out, and I don't know what the hell's going on. So I give my boss a call and say, hey, Mark, have you ever seen this problem? I've changed this 3 times, and this is the 3rd time I'm back here. What's going on? He says, yeah, look at the flipper coil on the opposite side. The diode is open on the other side. Here's what happens. When the diode opens, and this is very common, the diodes just physically break. Because of all the vibration on a flipper coil, the diode will just crack like that. When the diode on the opposite side fails, open circuits, every time you hit that flipper, every time you hit the flipper button on this other side, it's generating that 1,000-volt spike or whatever that travels along the power lines and goes right to the other diode, which is only a 400-volt diode, shorts the other diode. Well, shit, the left side is working. Why would you even look at that flipper? You never would. And I never did either. I didn't look at it. So the point I'm making, the bottom line is this. When you get to a pinball and you have a shorted flipper diode, meaning the coil looks perfectly okay, but it just blows the fuse, always physically visually examine the diodes on the other flipper or flippers, because there may be more than one flipper. Like this game has 4 flippers. Examine the diodes on all the other flippers and see if the diodes on the other flipper are open. Yeah.
Does that also can happen on the newer games where the fuses are separate?
Oh, sure. It happens on the new games, too. Even though the fuses are separate, that high-voltage spike still travels along the same lines through the fuse.
Me with D2, and I couldn't believe
That happened to you?
Yeah, it's just...
Now, here's what I do now that I've learned my lesson the hard way. Whenever I have a blown diode on a flipper, not only do I visually inspect all the flippers and all the diodes, but I physically push on the diodes with my thumb. I just raise the play field, I look at them, I just give them a shove with my finger or my thumb, because you'll find that a lot of times they'll just go crack, and they'll just crack right in half. You may not be able to see the crack until you push on it, and the diode will just go like this, and it'll just break right in half, and that's what's really wrong. But the confusing part about it is the original bad problem with the open diode, that flipper's working perfectly okay. So you wouldn't even think to look at it, and I've seen this problem dozens of times since then. In fact, as I told this story to one group in Dallas, Or maybe you know Polly. She works at Commander Ragtimes, I think, or whatever it is in Dallas. Okay, she was in the class, and I'm telling this story, and she's going like this because what they had the same problem. What they did was they kept replacing the diode with bigger and bigger diodes. They put the 400 volt diode would fail, and of course, and then they put a 1000 volt diode 1 amp. Then they put a 1000 volt 3 amp diode in. Then they put a 1000 volt 6 amp diode in there, and they were still changing it every couple of weeks. They couldn't figure out why that one diode kept failing. So that's really important. I've seen it a bunch of times since then. So again, one more time, whenever you have a blown flipper diode shorted, always look at all the other flippers and all the other diodes, see if you have an open diode. Does that make sense?
Yes.
Okay. Now let's take a look at the lamp circuits. The lamp circuit is also a matrix, and it hardly ever fails. Oh yeah, turn to page R25. What the hell? Just for reference so you know where to find this in the future. Although, to be honest, that schematic's kind of dinky. The lamp is also a matrix. For the same reason, we have 64 lamps. So the lamp is also a lamp matrix. And here's the way the lamp circuit works. Very rare failure, but here's the way it works. Each of the columns this time is connected to a transistor that is a PNP transistor. This is just about done. So each of these PNP transistors is connected to the lamp power supply. The positive voltage, there's a power supply in there, it's about 18 or 20 volts or something like that. That's the lamp power supply. So each of the columns is connected to one of these transistors. Each of the rows is connected to a ground switch transistor. An NPN transistor that connects to ground. Like that. And the lamps are connected in between the columns and the rows. And there's also a steering diode in these as well. A diode that I never see fail. These columns are called the lamp strobes, S-T-R-O-B-E-S. These are the strobes. They're called the strobes because you know how a strobe light flashes on and off like that. Flash, flash, flash. Well, that's what these are doing. One at a time, these transistors turn on and send a pulse down each of the columns. And you can see that the current will follow the arrow, won't it? Like that, right straight down the column. And every thousandth of a second or so it does is over and over again. It's strobing each of these lines. Well, let's say that the computer wants that lamp to light up right there. At the time that this strobe is activating, sending the current down that column, the computer will also energize this transistor. Now the current flows down the column, through the lamp, through the diode, it's facing the right direction. There's the ground switch, right to ground. So in other words, the computer is always strobing, always, every thousandth of a second, does that continuously. When it wants a lamp to turn on, it energizes that transistor and the current flows through the lamp and through that transistor to ground. The lamps in the playfield of the pinball machine are actually flashing on and off very fast. They're actually getting a bunch of little fast pulses. But of course, the filament stays lit up, it stays hot, so it looks like it's continuously on to us. And it really is continuously glowing, but it's glowing by virtue of the fact that there are lots of really fast pulses going through it, really. Well, these are called the lamp returns, LR, lamp returns, and there's eight strobes, and there's 8 returns as well. And if you look at page R24, you see the lamp matrix here. Look at the lamp matrix table. When you have a problem with the lamps, you're going to, if you have a semiconductor failure, that is, if one of the strobe transistors fails or one of the return transistors fails, you will have 8 lamps that are affected. You'll either have 8 lamps that never turn on or 8 lamps that are on real bright, one or the other. Let's say we have a problem with the following lamps, 25 through 32. What's common to all of those? Q60, yeah, column 4, right in the upper right-hand corner, it says Q60 is bad. I'll show them to you in just one second. If you have a problem with lamps 3, 11, 19, 27, 35, 43, 51, and 59, that's row 3, right? Q82 is bad. Like I said, Williams is the greatest. They really make your job real easy. Let's take a look at those transistors, shall we? And those transistors are right here on the board. They're in this area right here. And here they are. Here's Q52, 54, 56, 58, 60, 62, and so on. And then here's, Q80, 81, 82, 83, 84, and so on. I almost never see these fail. It's very rare to see these column or these strobes, I should say, or the lamp returns fail. It's just very rare to have a lamp failure. Now, typically what happens is this: you get to the game, and since transistors usually short collector to emitter when they're on, usually your problem is that the lamps are staying on all the time or very bright, in fact. And typically what happens is you get to the game and you see that there are a bunch of lamps that are out, that are burned out, and you go and you put new lamps in, and as you put in the new lamps in, wow, these things are really bright, aren't they? Then you notice that they're incredibly bright. Usually by the time you get to them, they're burned out, because they're so bright they burn out right away. So you get to them, you start putting them in, you notice that they're real bright. Don't say, wow, those are bright, well, but they're working, see you later, bye, because they're just going to burn out in just a matter of hours probably. You do have a problem. Look to see which lamps are the really bright ones. And you can put the game in a lamp test procedure that flashes all the lamps, and it's pretty obvious which ones are the bad ones. Something's wrong with this game. What's wrong with this game? No score displays. Okay, they're out, right? The score displays are powered by the high voltage power supply that's up here on this corner of the board. There's a plus 100 and a minus 100 volt power supply up here. If I set my meter to read DC volts, ground the black lead, just find one of those ground braids somewhere and jam it in there. Up here is the connector in the upper left-hand corner of this board, where you're supposed to have the voltage. And there's my plus 100, plus 99.6. That's fine. My minus 100, in fact, at this point, it looks like it's non-existent. It isn't even there anymore. When we first turned it on, I had about 30, 40 volts out of there. Now it's gone completely. Wait, let me just double check that, make sure I'm on the right connector. Yeah, it ain't there at all now. Unless I'm simply not touching it properly. Yeah, it's gone completely. No, it's minus. It might just be a bad connection here. Huh? No, it's not happening at all. Anyway, there's so obviously we have a problem with our minus 100 volt power supply, and in this case, I've always found it to be the Zener diode, the 100 volt Zener diode. In fact, before we leave here today, we'll change that Zener because you have it here. We'll see if that fixes it. That's a fairly common problem. In fact, it's like a very common problem. So that's that. In fact, that's the only thing I ever see go wrong. When the score displays don't work properly, basically you have one of the plus or minus 100 volt power supplies is bad.